Swayam Prabha. Digital India. Educated India.
This maritime engineering, as you see, is a very special program which has got multidisciplinary input from mechanical, civil, structural, aerospace, naval architecture, chemical engineering, electrical, electronics, applied mechanics. It's a multidisciplinary program. You will find this program is completely different, dedicated to industrial training and thorough capacity building on the new trade of maritime sector. It's a grooming economy which will give you a lot of job opportunities and research frontiers as far as India is growing. And the Blue Corridor effect, which is planned by Government of India, is one of the important mission which requires maritime engineering growth to happen in the country. So this program caters to expected that capacity building in this program.
Friends, this is part of a material science engineering laboratory which becomes one of the teaching aid for the maritime engineering program. So when you talk about materials innovation in maritime industry, though concrete and steel have been conventional candidates of choice for engineers, for example, we have titanium vessels, high-speed craft boats made of fiberglass. These are all advanced materials which actually do not come across conventional standard design code of practices. We conduct box furnace test, tube furnace test, vacuum arc melting, induction melting, vacuum induction melting, vacuum sealing unit, which are all present in this laboratory is a small segment of material science laboratory. Friends, a typical furnace where the operating temperature for testing specimen can go as high as 12 degrees Celsius. Generally at room temperatures and ambient condition, the mechanical properties will not alter much. As you see in the course lectures, you will notice that strength of the material get degraded when the temperature rises beyond 600. Therefore, when you talk about fire resistant design, you must also choose an alloying element such a manner that the strength doesn't degrade beyond 600 degrees Celsius at all. Welcome to the ambience of IIT Gandhinagar Lecture Theatre. This is one of the interesting classrooms where the maritime engineering classes will be conducted. We have got state-of-the-art projection facility and good audio-visual recording systems. Once the lecture is over, you see the system here. We can generate the PDF files of the lecture directly and you can email the PDF files directly to your email IDs. So it's a state-of-the-art facility we have in IIT Gandhinagar where the lectures are lifetime recorded and shared with the students immediately. This is the IIT Gandhinagar library. This has got all collections of books which are referred as the standard textbooks and references for the course and the program. It also has lot of online editions of design code of practices and reference materials and e-collections of various video lectures of international courses and programs related to maritime engineering. We will be taking you around to the advanced material manufacturing units. So you will have state-of-the-art facilities available at IIT Gandhinagar. So welcome to the program to join MTech and PhD at IIT Gandhinagar Maritime Engineering. So please try to enjoy and take the advantage of this to the maximum. Welcome to the program and welcome to IIT Gandhinagar. Friends, welcome to the lecture on maritime structures under fire, blast and explosion, organized and conducted by Department of Maritime Engineering at IIT Gandhinagar. My colleague Professor Gaurav Srinivasan is coordinating this course along with me and will explain and make some presentations on structural fire engineering as a part of this course later. So in lecture number 5 today, we are going to understand in detail about materials that are recommended and commonly used for maritime construction. It's a sequel lecture. So lecture number 1 on materials, which is slated as slot lecture 5 under the course maritime structures under fire, blast and explosion. Before we ask a question, why material selection is a complex task? Why material selection is a complex task? Why this is not the same story when you choose material for any engineering construction? For any engineering construction, you will always use the codal provisions for design, which usually recommends strength based design. Of course, there are methods related to performance based design as well, but usually material properties govern the design, and of course the design is also governed by sectional properties, because we worry about E, I, A, etc., moment of inertia, area of cross section, modulus of elasticity. So, material property and geometric or sectional properties usually govern the design, whereas in maritime structures you have one more additional relationship with the design, which is form dominance. Once we say form dominance, we allow structures to remain flexible. These flexible structures will undergo large displacements. Therefore, apart from designing the system to withstand the loads, you should also have to check that the displacements on the system does not exceed the limits. You may ask me a question, it is also common when we, for example, design a beam, we also check for vertical deflection, and then we check that the deflection cannot exceed span by 325, span by 250 as limiting factors given in the design codes. I agree, they are all member displacements. Here we are talking about rigid body displacement. The whole system, whole structure will get displaced. Okay, rigid body motion we call. So, here the rigid body motion for flexible structures are fairly large, which is not covered under the scope of conventional design where these properties are adhered. Therefore, when we talk about a system of that order which is permitted to have large rigid body motion, then do material selection play any role in designing or constructing, fabricating the structures? The answer is big yes. Therefore, we need to understand the choice of material for this kind of construction, and we all know as engineering graduates, all materials do not fulfill such special requirements. Furthermore, friends, we are also looking for accidental loads mitigation or reliable design, where the structure will be now under fire, blast and explosion. So, the material degradation takes place very severe as you go ahead with the high temperature. So, therefore, all material cannot sustain the strength ability to withstand the forces or loads at high elevated temperatures. So, again under the comprehensive view of fire, blast and explosion models, choice of material also still plays a vital role. So, when you talk about this particular content of the course and further, there are some good references which I would urge that you should follow. Fire resistant design of structures by CRC, myself and Professor Gaurav, design aids for offshore structures under special loads with multiple authors on board, published by CRC. Then offshore complaint platforms which will help us to understand the design with large displacements, published by Wiley. Dynamic analysis and design, published by Springer. Design aids of offshore structures, published by Springer under fire resistance. Risk and reliability assessment, published by CRC. Some of these books which is slated there on the screen may look very useful references for you to reinforce your learning as we get along with this course. Of course, the fundamentals of maritime structures in terms of geometric form, material for construction, construction methods, fabrication, installation, decommissioning, commissioning can be looked at. These books of ocean structures and materials by CRC, and advanced marine structures again by CRC, and fundamentals of offshore engineering again by CRC, authored by multiple authors along with me. So, friends, have a copy of this book, refer to your library and keep referring them for your class notes as well as future lectures in this particular content of the course. Now, let us go forward and ask a question: what are various functions for which a maritime structure is constructed. We discussed about that in the previous lectures. Just to reiterate what we have learned, maritime structures are constructed for various functions. The foremost function, which is very useful and unique, is oil and gas exploration and production. Of course, offshore structures are constructed for this very purpose. In addition to that, we also construct structures for wave and wind energy harvest. Wave energy devices, offshore wind turbines, so these are all structures constructed for wave and wind energy harvest. In the previous sequel lectures, we understood that there are some structures constructed for coastal protection, and these structures, all of them put together, demands repair, inspection and regular maintenance at periodic intervals. Okay? Functionality, material property, environmental context and technological advances govern the geometric form of design. However, when the structures are subjected under repair, then the downtime, it may be because of maintenance or because of repair, could cause a huge financial loss, because if offshore platform or coastal structures are not remaining in operation for any specific reason due to their maintenance or repair, then the downtime of these kind of structures caused huge financial loss. So, one has got to be very careful in planning periodic maintenance as well as carry out repair when the structures are loaded. Remember that generally we do repair and retrofitting after relieving the loads from the structures, but in maritime structures this is not possible. These structures will always remain under categoric loading, especially from waves and wind and current, etc., even if you do not load them by dead load, impact load and imposed loads. So, structures, when they are exhibited and placed in position, when they are loaded, they will be undergoing or undertaking repair. So, be very careful about choosing the material even for construction as far as for repair, because these structures are generally repaired when they are in service. So, repeated visits to maintain their functionality are not in the main agenda of the structures, because most of the structures are unmanned or very few people will be kept on board, maybe even on coastal side, to visit or to look at the maintenance perspective of these kind of structures. Okay? So, the maintenance purpose perspective for checking their functionality are not actually in the main agenda of maintenance. In such cases, a continuous monitoring scheme is necessary to ensure proper functioning of these kind of structures. Okay? So, these structures demand usually something called preventive maintenance while the systems remain functional. Structural repairs should be carried out without shutting down their operations. Most importantly, these structures need to be repaired when they are loaded. That is very important. Hence, the structural forms of these systems should be simple with easy to inspect and maintain. So, materials of this catering to these special requirements are only the subset of our discussion today. We cannot therefore use all kinds of materials. We cannot also use advanced materials without putting them to test in maritime environment. So, we have very limited choice of material which can be recommended to be used for construction of maritime structures. This is the reason why we have to be very careful in choosing the materials before understanding their classifications and structural properties, as we learn from this point onwards. Furthermore, friends, maritime structures operate under very high risk factor. The reason is they are exposed to exploration and production processes. Hydrocarbons are most vulnerable explosives. Therefore, these structures are always under susceptibility or vulnerability of fire, explosion and blast loads. Their failure may lead to serious environmental pollution and huge economic losses. So, one has got to be very careful that the structures should not encounter catastrophic failure under any accidents. To avoid such consequences, it is always better to follow a preventive maintenance approach rather than we make an approach in terms of maintenance as and when required, which we generally do for land based structures. So, preventive maintenance will come only when the structure is subjected to continuous health monitoring under time varying loads, because wind, wave, current, earthquake, seaquakes, etc. keep on varying as we proceed further to do them under construction. So, the preventive maintenance approach is successful only when the structure is undergoing continuous health monitoring. So, therefore, friends, material selection is a very challenging task. The simple reason is no single characteristic of the material helps to rank them. For example, if you have got different materials of similar characteristics, then one can rank them and choose the best out of them, whereas in maritime industry it is not true. Material selection is not dependent on single characteristic, but depends on the functional characteristic of the structure for which the material is demanded. So, same material for different forms of structure, different material for same form of structure, different material for different members of a structure are all very special applications as we go ahead and see now. The basic knowledge about mechanical properties of materials help us to choose an appropriate material. So, therefore, we are now urging to learn the basic mechanical properties which will govern us to choose material for maritime construction. Having said this, let us now ask a question: what are the major factors should be considered in choosing material for maritime construction? So, let us look at these factors. Factor number 1, physical and chemical properties of the material. Of course, factor number 2 is economy. Third factor, whether the material is fabricatable, can we weld the material together, fabrication facilities, and then what is the expected maintenance cycle of the material. Okay, material degradation under marine environment, which is corrosion, which is one of the most serious and heinous problem with materials in maritime structures. So, therefore, what is the expected maintenance cycle of the material being used? If you use steel, it has got a different cycle of maintenance. On the other hand, if you use concrete or any functionally graded alloys, then the maintenance cycle is different. So, one should consider the following factors like physical, chemical properties, cost, fabrication facilities, and expected maintenance cycle before we decide any material for maritime construction. So, this complexity was not there, was not realized when you use material choice for construction based on land. When you go to maritime industry, then this issue is more governing. Therefore, friends, one important task what an engineer should keep in mind is that material whatever you choose should avoid catastrophic failure. Material should not fail without any warning. So, from the basic principle of mechanics, if you try to understand this, material failing with warning means what? Material should give us sufficient time lag before it fails ultimately. So, what we call this technical point in the design as ductility. Okay? Material should give sufficient warning before it fails. It should not be a brittle material, because brittle materials fail catastrophically suddenly without warning. So, I cannot use or afford to use a brittle material for maritime structures for a simple reason: I need some sufficient time to gain the retrofitting and repair operations to make the structure in position or place the structure in position. So, therefore, material should be chosen to avoid catastrophic failure. In addition to that, of course, this material should meet the design requirements. Okay? And most importantly, when you choose any material, the material should be able to withstand hazard loading. All materials are not good at impact loads. Okay? Inundation is a very serious issue on certain class of materials. So, material chosen by you should be also able to withstand hazard loads. So, then under these complex thinking, let us list the important properties material should possess if I have to use it for maritime construction. The foremost property, as we all know, the engineering property, is the yield strength of the material. This is the first consideration. Second, of course, in the order is the modulus of elasticity, since deflections and bending in the structure becomes very important. Since we are talking about multi-axial loading, therefore, I must look at Poisson's ratio effect on the material and there is always a possibility of the material or the member being subjected to reversal of stress cycles. So, the material should also have good fatigue performance and fracture resistance. So, let us see the important properties which I must think about. I am saying structural properties which I must think about. One, of course, the yield strength. The yield strength should be as high as possible for a given material or chosen material. It should have very high modulus of elasticity. Okay, it should have very high. Generally, steel has a very high modulus of elasticity. It's 210 megapascal or and so on. Material should have good Poisson's ratio, because we are talking about multi-axis loading. Because wave direction, wind direction, current, sea quakes, earthquakes can affect or attack the member of the material or the design of the structure from any direction. They are randomly varied. So, I should look for multi-axis loading. So, Poisson's ratio should enable uniform distribution of stresses along and across the thickness of the member. The fourth, of course, should be the material should have good fire resistance characteristics, and it should also sustain impact loads, because blast and explosion cause huge impact on members. With all that, we never underlying saying that cost should also be an important factor. Okay? Since the material or the member is under reversal of cycles, I should look for very high fatigue resistance and fracture resistance. A long list, friends, a long list. Okay? Out of all, the primary factor which will govern the whole choice is Young's modulus, yield strength. The first preference or the first level of choice is given to yield strength. Okay, followed by Young's modulus. Friends, why are we concerned about the mechanical properties of the material so much? Because mechanical properties actually reflect the capacity to resist various types of loads. A few of them are strength, hardness, elasticity, plasticity, brittleness, ductility and malleability. Common types of stresses which occur in members of maritime structures are compressive, tensile, shear, torsion, impact or combination of them. It can also be resulting from fatigue stresses. Strength, of course, is a very important property of the material which enables the material to resist deformation under loads. Ultimate strength, of course, corresponds to the maximum strain level that the material can withstand. Some materials are equally strong in compression and tension and shear. However, many materials show different marked differences in tension and compression. For example, cured concrete has a maximum strength of 50 megapascal in compression, but only 3 megapascal in tension. So, concrete has a different strength aspect in compression and tension. Carbon steel has maximum strength about 400 megapascal in tension, but when you apply compression, tension and compression, but when you talk about shear, the maximum shear strength is only 290 megapascal. So, therefore, friends, while dealing with the maximum strength, it is also necessary to always state the type of loading for which we are looking at the design. A material that is stressed repeatedly under reversal of stresses or nature of loads fails at a critical section. Stresses at critical section therefore at a time of failure are considerably much lower in amplitude compared to the maximum strength of the material, be it tension, be it compression or shear. Therefore, friends, in fatigue failure, it is not the amplitude of the load which is important, but the number of cycles compared to the nature of load. Okay? So, if it is a cyclic loading, it is the number of cycles which will govern the load corresponding to the cycle for failure. Let us look at some of other properties which are also equally important before choosing the material for maritime construction. Hardness. It is referred as an ability to resist permanent inundation on the material. As there are several methods of measuring hardness, it is always specified in terms of a particular test which is used to measure hardness. For example, Rockwell, Vickers, Brinell are different methods by which I can measure hardness are some of the common methods. Usually Rockwell hardness is commonly used for specifying hardness for material of steel used in maritime structures. Toughness is equally important and considered as a combination of strength and plasticity. When a material is subjected to load of known magnitude, it causes deformation to the member or the material. Elasticity is the ability of the material to regain its original shape and size upon removal of load. Therefore, friends, limit of material up to which the material remains elastic which can be loaded is called the elastic limit of the material. Plasticity is the ability to deform permanently, but without breaking or rupturing. This property is opposite to strength. By careful alloying of metals, the combination of plasticity and strength is used to manufacture marine steel. So, for maritime construction, a special grade of steel is generally recommended. Now, as we understand now slowly, steel fulfills most of these requirements. Let us talk about steel much more in detail. Steel alloys are preferred to construct fixed offshore platforms, maritime structures where strength and stiffness both are equally important in comparison to the weight reduction. Properties from corrosion resistance to high tensile strength depend on few factors: the alloying material, percentage carbon present in the content of alloying, and heat treatment methods. Two common examples of steel alloys is low alloy steel and high strength alloy steel. Low alloy steel, which is usually iron based alloy, is hardened to gain higher strength. A common steel alloy has a strength in the range of 1242 megapascal to 1379. This is referred to as AISI 4130. Another type of AISI is 4340, where the strength ranges from 1379 to as high as 1931 megapascal. When you talk about high strength alloy, which belongs to a family of 300 M, which can be used to meet the strength requirements exceeding 2000 megapascal. This family of steel very corrosion prone and must be electroplated to avoid corrosion. So, as you gain on one front, you lose on another front. So, one has got to be balanced in choosing material carefully for maritime application. Now, let us see how steel is classified before we choose a material. Steel is classified in many ways based on composition of alloy, based on manufacturing methods, based on finishing methods, based on product form, based on microstructure, based on strength level, and based on heat treatment. There are many ways by which I can classify steel. Let us say, based on strength, they are classified as low, medium, and high. Low strength steel has an yield strength up to 415 megapascal. Okay, the yield strength is less than or equal to 415 megapascal. They have very special applications. They are used for manufacturing, fabricating hull form of ships, fittings and fasteners, tank instrument fittings, and buoys. They should meet ASTM A242 standards before they are tested and used in maritime construction. Medium strength steel has an yield value less than 1035 megapascal and of course greater than 415. They are widely used in construction of icebreakers and buoys in Arctic region. So, the strength of yield can be as high as about 1035 megapascal, which is a big number. High strength steel of course has yield strength greater than 1035. For example, a special variety of maritime steel can even have strength of about 1 to 2 gigapascal, which is used for special applications in maritime structures. Now, based on tensile strength, I can also group steel as 1, 2 and 3. So, group 1 means strength, yield strength less than 275, group 2 means yield strength is between 275 and 415, and group 3 means is between 415 and 690 megapascal. So, according to American Bureau of Shipping, condition for classification of unit structures also depends on fundamental requirements of material selection. Now, please see this table. The steel is grouped as 1, 2 and 3 as you see here. Okay. So, various applications are also listed. So, same group, there are many categories of ASTM which will fill up the standards. So, the yield strength and tensile strength vary significantly friends within the same group. Okay. Of course, when you move from group 1 to group 2, it varies much significantly. Further with group 3, it goes very high. Okay. So, that is what we say categories of 275, 275 to 415 and 415 690 can be grouped. So, this is one way of again classifying steel for maritime construction. So, what are the fundamental requirements we must consider for material selection? Apart from the engineering properties, we should also think about formability, weldability, strength, toughness and corrosion resistance. So, these are all additional properties which one must look at before choosing material for maritime construction. In addition to this friends, as I said, toughness is also a very important check to choose material for maritime construction. This should be exhibited based on Charpy's toughness test. Based on this, steel can be further grouped as 1, 2 and 3. For example, group 1 has thickness from 6 mm to 19 mm whose energy absorption is 20 joules based on Charpy's test. If you have chosen a material whose thickness is more than 90 millimeter, then the energy absorption requirement is 27 joules. Similarly, when you talk about group 2 and 3, thickness can be more than 6 millimeters, but you expect to have the Charpy's impact test value more than 34 joules. So, depending upon the toughness index also, steel is grouped. So, based on tensile strength, steel is grouped, based on toughness strength, steel is grouped, and we also group steel based on through thickness stress. Okay. For members with applied loads normal to the surface, special steel with improved through thickness stress thickness is being used. One important aspect about Charpy's test which we all know is a good indicator of toughness, but this test is conducted at a specific temperature. Okay. The test temperature is about 30 degrees Celsius below the minimum service temperature to which the structure is subjected to. Service temperature for members below splash zone is 0 degrees. For member within splash zone, it is the lowest atmospheric temperature. We all know what is the splash zone. If an offshore structure is constructed let us say a jacket platform, this becomes the mean sea level, this is marked as water depth. So, this is what we call as splash zone. Corrosion is maximum here because of differential aeration. This is called atmospheric zone and this is called immersion zone. Okay. Here as we go deeper and deeper, corrosion will be lesser. So, the corrosion is maximum at the splash zone. Having understood this, so when we are using members at splash zone, then you must conduct this test at a temperature which is actually the lowest atmospheric temperature at that location. If you have thickness of the members less than 6 mm, which is very unusual, you need not consider impact test requirements at all. Okay. Friends, mechanical properties of material or steel vary based on the chemical composition, heat treatment and manufacturing process. Strength can be increased by adding alloys such as manganese, niobium, vanadium, where ductility, toughness, weldability will be compromised. So, therefore, friends, if you have different alloying elements to steel, the property of steel, the engineering property of steel varies significantly. Okay? For example, if you minimize sulfur, it improves ductility. If you add nickel, it improves toughness. Therefore, friends, it is very important to arrive at carefully balanced chemical composition to achieve the desired structural characteristics. Heat treatment, manufacturing process are of critical importance to this performance. Rolled or formed steel members show higher strength, but increased thickness shows reduction in yield value. Effect of heat treatment deployed in steel manufacturing also helps and govern its strength and toughness. Now, let us see how steel is classified based on the manufacturing process, which is a strength dependence process. The common manufacturing processes are as rolled, normalized rolled, thermomechanically rolled TMR steel. You must have used in the commercial market, people use TMR steel, this thermomechanically rolled, and quenched and tempered steel, Q&T steels. These are all various classification of steel based on the manufacturing process. Friends, steel cools as it rolled with a typical rolling finish temperature at about 750 degrees Celsius. If it is allowed to cool further, naturally, then it is called as rolled steel. Normalized steel is manufactured by heating as rolled steel up to 900 degree and held at temperature at the specific time before it is allowed to cool. That is a general manufacturing process of steel. Normalizing refines the grain size and enhances toughness. Normalized rolled steel is manufactured by rolling a steel at a temperature greater than 900 degrees Celsius, which eliminates the extra process of reheating the material. Normalized or normalized rolled steels have designation called N. So, this is an indicator that the steel is normalized and normalizedly rolled. Thermomechanically rolled steels, TMR, is a very special kind of steel which is also used in maritime industry and is manufactured at a lower rolling finish temperature about 700 degrees Celsius. They are classified as M grade steel. So, we already seen what is N grade steel. N is normalized and normalized rolled steels. Normalized in sense you heat that steel for a specific temperature, retain the temperature for some time, then naturally cool it. That is called naturally cooled or normalizedly rolled steel. In addition to this, friends, quenching and tempering processes in manufacturing also help us to achieve higher strength of steel. Q&T steel is manufactured at about 900 degrees Celsius, which is rapidly cooled or quenched to produce steel with high temperature, strength and hardness. But this kind of steel has very low toughness. They are classified as Q designation steel. So, we have got M grade steel, we have got Q grade steel, we have got N grade steel and so on. Quenching involves cooling a product rapidly by immersion directly into water or oil. Tempering is the second stage of heat treatment to temperatures below arsenic range, which softens the steel. So, tempering will help us soften the steel and quenching will help us to add strength to steel. It also make it tough and more ductile. Use of high tensile steel can of course reduce volume and design of steel, but steel needs to be tough at operating temperatures. So, toughness is also equally important compared to its strength. So, friends, if we look at this curve carefully, different varieties of steel plotted for stress strain curve. Let us look at carbon steel, the green one, okay, which has got a very phenomenal strain, but a very limited yield value of 276 megapascal. If you look at stainless steel 304316, which has got good corrosion resistance, but the yield or the ductility is poor and the strength is almost much lesser than carbon steel. But if you use stainless steel of 2205, it has got a very high strength as well as good ductility or strain limits. So, depending upon what alloying elements used in steel, can always increase the strength, increase its strain value and ductility limits as you choose. Let us look at this table. What is the minimum yield and tensile strength that is required and preferred for hot rolled steel? So, friends, if you look at any grade of steel, let us say S275, S355, these numbers actually refer to the yield strength. Okay? But yield strength also depends on the nominal thickness of the member. If you have got any material or member thickness less than 16 millimeters, then these numbers correspond to yield strength directly. However, when you use a thicker material varying from 16 till as high as 100, then this strength varies. Okay? So, you must choose steel not only with classification, but also what thickness of the member you want, because the strength for the design varies with thickness as well. Of course, this variation is less when you talk about tensile strength of steel, which varies from 100 to 150. So, they are all higher than this kind of steel. Okay? So, higher strength steel require improved toughness and ductility, which can be achieved only by low carbon steel under thermomechanical rolling. So, people pick up low carbon steel, do TMR rolling to achieve high strength steel. The table shows the minimum yield requirement and tensile strength requirements of commonly used hot rolled steel grades in structural design. S designation indicates in the table as carbon steel, like M and N, you also have S, which refers to carbon steel. The minimum yield strength and tensile strength are taken as characteristic yield and characteristic ultimate strength for design purposes. So, friends, let us go to the summary in the last lecture. In this lecture, we learnt what are the important factors that help us choose materials for maritime construction. The various engineering properties govern this choice. They can be also listed, but we understood that no single property is useful for all applications in maritime industry. Okay, so it is actually a property is operation or structure specific. Furthermore, friends, we understood that the structure should possess special properties to withstand loads even under repair, because the downtime will cause economic loss. Okay. Looking at these details, we understood that few properties are very important for choosing steel. One is the yield strength, other is the modulus of elasticity, Poisson's ratio, and then its fire resistance, toughness, hardness, and ductility requirements will help you to choose appropriate steel for maritime construction. We look forward some of more material properties and their choices and their strength variation at high temperature in the next lecture. Thank you very much. Namaste.